See, so far what we have, the understanding that a autonomous system, it is given to us in the form of, suppose dxi dt, it is function of xi comma t. Okay, autonomous system, and corresponding to that autonomous system, but we have one matrix representation that is given by, here we already had this idea, that is x dash is equals to a x. Okay, so corresponding to one autonomous system, we have one matrix representation where this a, it is nothing but the coefficient matrix, and this x, it is the corresponding column matrix which is generated from the given x1, x2, x3 and so on, these values. Okay, so one example we can take. So for example, suppose one system, it is given as, let one system is given by dx1 dt is equal with x2, and dx2 dt that is given by minus x1. Suppose this is given to us. Okay, so basically this is the system, that is dx1 dt is equals to 0 x1 plus x2. You can write like this, dx2 dt that can be expressed as minus x1 plus 0 x2. So corresponding to this, but we have the expression as dx1 dt and dx2 dt. This one, it is 0 1 minus 1 0, and here we have x1 x2. So this is nothing but x dash is equals to a x, where this a, it is given by 0 1 minus 1 0, and x, it is given by x1 x2. So we have a system, and corresponding to that, this is the setup. Yeah. Okay, now one system is given by this one. Check the system is stable or unstable. Okay, so this stability criteria, how we can determine, it is completely governed by the concept of eigenvalues of this matrix. Okay, so we need to find eigenvalue of this matrix. Find eigenvalue and check or do the analysis. Okay, do the analysis. So how to do the analysis? So for that, we have few important results. So before going into that, suppose what do you mean by the stability or instability situation? Suppose we have one scenario where yt, it is given by, suppose c1 e power minus t, this one. Okay, suppose we have this one. Okay, so in that case, just see the situation. If you try to draw the graph of this, you have something like this. Okay, so it has a tendency to move towards or to approach towards this x-axis. Okay, isn't it? So as t tends to infinity, yt, it is approaching towards 0. Okay, yt, this value, it is approaching towards 0. So it is the case for stability. Okay, so the corresponding system for which we have this as a solution, so that system will be stable. Okay, stable. Whereas if we have, suppose the solutions are like this. Suppose this is also a situation where we can have a solution like this, which is approaching towards this x-axis. Okay, like this way. This is also a case for stability. Okay, this is also stable. So this is the case for stability. Whereas if we have, suppose yt is equals to, suppose c1 e power t, so it is clearly visible that it is nothing but a exponential growth. So exponential growth, this type of graph you'll be getting. So exponential growth. So in that case, the system, it is not stable or unstable situation. Okay, the system will be unstable. So this is more or less the idea for the case of stability or instability. Now there are few formal results. So let me note down, or let me give those results for you. So first thing, it is classification, eigenvalue based stability classification. Okay, so first is asymptotically stable. Asymptotically stable. So what do you mean by asymptotically stable? That means solution decays. That means here solution decay to zero as t tends to infinity. See, all the system whatever we are considering here, they are nothing but autonomous system. That means dependent on, that means x1 x2 or whatever the variables we have, they are dependent on t. So the solution decays to zero as t tends to infinity. This is asymptotically stable. So in this case, all the eigenvalues, so in this case the result says that all the eigenvalues must be negative, or if you are getting complex eigenvalue, then their real part, if complex eigenvalues we are getting, so real part must be negative. Okay, so in that case we have asymptotically stable case. Okay, so this first example whatever we considered here, this was the case for asymptotically stable situation. Now second one, it is unstable. Okay, so unstable here, that means here at least one eigenvalue must be positive, or the real part of at least one eigenvalue, obviously this should be positive. That means one eigenvalue has a positive real part in this case. Okay, so here you can note down this, at least one eigenvalue must be positive. Okay, so this is the case for unstability. And third, we have another situation which is known as marginally stable, or it is known as sometimes neutrally stable. So here all the eigenvalues, they have non-positive real parts. Okay, non-positive real parts, that means purely imaginary. So in that case what you have, purely imaginary. Okay, purely imaginary. Non-positive real parts means purely imaginary case. Okay, or it can have negative real part as well. Okay, negative real part as well. So non-positive. So in that case what you have, see, marginally stable situation. So here you can take example. So here this was our initial example. See this example here, you can just find the eigenvalues. So eigenvalues are given by a minus lambda I equals to 0, the characteristic equation we are going to find. So here what we have, see, so lambda, here you have minus lambda, and here 1 minus 1. So you do the calculation. So here lambda square plus 1, so we are getting lambda as plus minus I. So all the eigenvalues are complex. So here you can see real part of lambda, it is nothing but 0. So real part nothing but 0. That means the system is marginally stable. Marginally stable. Okay, so we have this situation for marginal stability. Similarly, another example if I give you, suppose check the stability. Suppose next example, check the stability of a system given by x dash is equals to ax, where a is nothing but minus 2, 0, 0, minus 3. Now see, here it is quite easy. See the solution, just by seeing the matrix A you can immediately tell eigenvalues. See here, this is a diagonal matrix, so eigenvalues are lambda 1 minus 2, lambda 2 it is minus 3. See all the eigenvalues, negative real part, negative real part, obviously both are real actually, so all are less than 0. So immediately you would claim the system it is stable. The system it is stable. Now here you can see, if you just find solution of this system, so immediately you will have some part like e power minus 2t, okay, and e power minus 3t. Okay, just apply the matrix method and try to get solution. You will get solution like this. So e power minus 2t and e power minus 3t. So here this one as well as this one both has a tendency to approach towards the real axis. Okay, that means tendency of decay is there for the solution as t tends to infinity. So we have the stability situation. Okay, whereas if I take suppose another example where here the matrix was this one, and second matrix, suppose if I take A is equals to 1 2 0 3, suppose. Okay, so in that case immediately see again what you have. See the solution here, the eigenvalues are given by 1 and 3. Again this is a diagonal matrix, not exactly diagonal. See you have upper triangular matrix, so 1 and 3 these are the eigenvalues which are greater than 0. Okay, so here what you have, as per our discussion, the corresponding system it is unstable. At least one eigenvalue should have positive sign, or positive sign. Okay, or one eigenvalue must have positive real part. So in that case immediately unstable. So here both you are getting as greater than 0, so unstable. Whereas here if you just go for the solution, you will find some term e power here, e power here. These terms are strictly greater than 0. So greater than 0 means you have the tendency of exponential growth. So you have the instability situation here. Okay, so this is the basic understanding of stability from eigenvalue criteria or eigenvalue analysis. Now the next part of this lecture will be dedicated to the another method, whatever just we discussed, that is matrix method, one method. Another method, it was a diagonalization method. You can see the playlist there, the last two videos are dedicated to one matrix method, another was diagonalization method. Now we will be discussing the next method, which is completely based on Laplace transform. Okay, so let me go to the next slide. So Laplace transform technique, but provided the initial conditions are given, okay, then only we can apply the Laplace transformation technique. So here we can have the method. So solution of a system of ODE, system of linear differential equation, linear ordinary differential equation, using Laplace transform, provided initial conditions are given. Okay, so here you can write one problem. Through that problem you can try to understand. So here solve x dash is equals to 2 minus 3 1 and 0 x with the initial condition x0 is equals to 1 2. So we'll try to solve this question using Laplace. Observe here, these are the initial condition, that means x1 at 0 it is 1 and x2 at 0 it is 2 given in the question. Okay, so we'll apply it, and if this is given in the question, then only you can apply this technique, otherwise it is not possible. Okay, so here we already know that Laplace transform of x dash t, what is the formula? S Laplace of x of t minus x of 0. This is the formula we have. So this formula, it is crucial, and we are going to apply this to solve this question. Okay, now see this system, it is given as x dash is equals to 2 1 minus 3 0 x dash. This is x, this is equation number 1, this is equation number 1. Now here you can see what you have, x1 dash t, x2 dash t, here 2 minus 3 1 0, here you have x1 t, x2 t. So if you apply Laplace both sides, what you have, see here Laplace of x1 dash t and Laplace of x2 dash t. Similarly here a, here Laplace of x1 t, here Laplace of x2 t. We have this one. Okay, so here let Laplace of x1 t, it is denoted by x1s. Similarly Laplace of x2 t is denoted by x2s. So here as per this setup, if you do the calculation, so what you have, see Laplace of this one means Laplace of s into, as per this formula s into Laplace of x1 t minus x1 0, and here what you have, s into Laplace of x2 t, here x2 0, here a times Laplace of x1, that is already we stated x1s, capital x1s, here x2s, capital. Okay, so what we have, see here, this is nothing but s, you can take common, and Laplace of x1 t, Laplace of x1 t and Laplace of x2 t minus here x1 0, here x2 0, you can write. So what you have, a x1s, here you have x2s, these are all capital, these are Laplace already we have. So s into, this is x1s, this is x2s, minus the values are already given, x10 and x20, so you can apply those values, 1 2, here you have a x1s, x2s. So now we're almost done. So s minus, can take this one here in the left hand part, so s into identity matrix minus a into x1s. See, we are doing matrix algebra, so that's why s into I you can write. So x2s, here we have 1 2. Now see, we are almost done for the first part. See, si minus a inverse, here we have 1 2. Okay, so you can make this one number 2. Now see, si minus a inverse, it is required. So first we need to find this si minus a. So this quantity it is given by 0 0 s minus a is 2 minus 3 1 0. So if you do the calculation, you'll be getting s minus 2 here 3 minus 1 s. Now immediately one can find si minus a inverse, that is adjoint of this, adjoint si minus a by determinant si minus a. You calculate the determinant and calculate adjoint and substitute here, you'll be getting 1 by s square minus 2s plus 3, and here you have s minus 3 1 s minus 2. Okay, so this is s minus a inverse. So if you substitute here in 2, so 2 will give you the next expression. So from 2 you'll be getting this quantity, see, x1s x2s, that is given by, here you have s minus 6 by s square minus 2s plus 3, and similarly 2s minus 3 by s square minus 2s plus 3. Okay, so here if you just compare component wise, so you will be getting x1s, that is s minus 6 by s square minus 2s plus 3, and x2s, that is 2s minus 3 by s square minus 2s plus 3. Now from each of this part you have to apply inverse Laplace, that means apply inverse Laplace and you will get x1t Laplace inverse, that is s minus 6 by s square minus 2s plus 3, and similarly here also you can do x2t, you will be getting Laplace inverse 2s minus 3 by s square minus 2s plus 3. Now you can do the calculation, and here see Laplace inverse, here what you have, s minus 1 square plus root 2 square, you can write like this, and here this part can be written s minus 1 minus 5, this part, and immediately you can apply linearity property, and you have s minus 1 by s minus 1 square plus root 2 square. This is one part, and another part you can write like this, 5 root 2, here Laplace inverse, here you have root 2 by s minus 1 square plus root 2 square. So apply the formula, so immediately you will be getting e power t cos root 2t minus 5 root 2, here e power t sin root 2t. Okay, so this is our x1t, this is x1t. Similar approach you need to apply here and try to get the solution. So x2t Laplace inverse 2s minus 1, here minus 1 by s minus 1 square plus root 2 square. If you do, so what you will get, see here 2 Laplace inverse, so first part will give you e power t, in case cos root 2t, this is the, and remaining here we will get 1 by root 2 e power t sin root 2 t. Okay, that is your x2t. Okay, so this is x2t, this is x1t, and this is our final solution. Okay, so this is how we can apply Laplace in the problem, and we can immediately get the solution provided initial conditions are given in the question. Okay, so likewise we can easily solve the question, but make sure the calculation it is accurate. Okay, then only we can solve, otherwise the calculation itself will get more complicated, and obviously will not get correct answers. So that's why you should practice and make your calculation skill accurate. Okay, so that's it from today's lecture, and I hope you got the idea of stability properly based on the eigenvalue analysis only, because that is a broad topic, but we are only restricted applying the eigenvalue concept. Okay, that is one part, and another is this Laplace transform technique. Okay, so thank you.